Okay, so again, continuing our journey using applications, we're going to talk about connected objects. So we had a little bit of preview of a connected object a couple of videos ago, when we found the tension between two blocks. Okay, but in this video, we're going to kind of focus around Atwood machines. Okay, so an Atwood machine is a device where two masses are connected by a string passing over a pulley. Okay, now they take various forms, right? So some things you have to understand is that the pulleys in the system is going to be assumed to be ideal, meaning that it's not going to contribute any kind of mass or friction to the problem. And then we have a modified Atwood machine is one in which one of the masses is going to rest on a table where the other one's going to be hanging. And that what rests on a table could be horizontal and it could be an inclined plane. Because the string of the machine is also ideal, the tension is going to be the same throughout the system. And that's going to be very helpful because we can treat this as a single system object or a single system problem where we can eliminate the tensions inside and just focus on what's actually going to pull the Atwood machine. And what happens is the acceleration, because it is a system, again, will be the same. And then another way to think about it is that each mass is going to have its own coordinate system. We'll talk about that here in a second. So here's the basic Atwood machine, okay? And so when we talk about, if we're going to do a single system problem, right, we're going to say this is my system, which would eliminate kind of any of these tensions that are going to run around in here, okay? In fact, one will be positive, one will be negative, right? And so I'm going to choose my positive in the direction, right, of motion. So I know this bigger block's going to move down and this smaller block is going to move up. So I'm going to call positive direction down, and then for my small block or my big block, and then on my small block it's going to be up. But remember, each object will have its own coordinate system, right? And so this will have a positive, this one will be positive down. So if I'm drawing the free body diagram, I have tension, and then I would have M1G. Here I have tension and M2G, but there'll be one would be T minus M1G, and then you'll have M2G minus T. Okay, but remember they're going to accelerate at the same rate. Now, if I want to choose this as a single system, the two objects the two things that are going to be pulling it is going to be, I'm going to have an M2G pulling it down, and I'm going to have M1G pulling it up. Okay, and so that will make my substitution easy. And a red flag, I'll do this in red, would be you will divide by total mass in fact, in every Atwood machine problem, okay, whether it be modified or a regular Atwood machine. Okay, now here's what a modified Atwood machine looks like. Again, table, right? So this will be a table, one mass hanging off. Each one will have their own coordinate system. And again, we'll choose positive in the direction of motion. But what happens is now I have to follow this through the incline or through the pulley, and actually causes my positive X to be pointed down. Again, but if we treat this as a single system, right, this will be single system. What's pulling it down would be the mass 2 off the table. And then nothing's really trying to hold it back, okay, unless you have friction. If you have friction here, you would have a friction force, which we'll talk about friction later. But then, okay, then I can go in and treat these individually like I did in that connected object or that problem before, where now I go look at the individuals where I can find tensions or things like that. Okay, so let's look at an example. So this one talks about we have two masses connected by a massless frictionless pulley and a massless string, assuming a frictionless surface, determine the acceleration of block 2 in the diagram. So this is block 2, this is block 1. Okay, but let's treat this as a single system. So my free body diagram, I would have total mass. Well, I know that this is block 2's weight is going to try to pull it down, and block 1's weight is going to want to try to pull it down the incline. Okay, and so excuse me. And so when we do this, now we're just going to simply say F2G, right? That's going to be, this is F2G minus FG1X, and that's going to equal to M total A, right? So mass of the total mass of the system. And so I'm going to have M2G minus M1G sine theta. Again, we have to do sine theta because this is the X component. That's the only thing that's trying to accelerate this down the incline, right? It's the only one that's pulling it down the incline. And it's going to equal to mass total. And so my acceleration is going to be, let's do a little factoring, or let's clean it up a little bit. All right, so I'm going to have G times M2 minus M1 sine theta divided by M1 plus M2, right? And so here's that red flag again, right? Wave the red flag. Remember, always dividing by total mass with Atwood machines. Okay. If we have friction running around in here, which we're going to talk about in the next video, right? Friction would contribute depending on where it's moving, either up the incline or down the incline. Okay, which changes will add another factor here, a positive or a negative friction value. Okay, so next thing we're going to look at is friction, and we'll talk about, and I think the example problem actually is this basic scenario with that added friction piece.